This is a pre-recorded poster presentation for the manuscript titled Liouville Flow Importance Sampler to be presented at ICML 2024. We're interested in the sampling problem where the unnormalized density function of a distribution is given, and we're tasked to generate IID samples of the distribution and estimate the normalization constant. The sampling problem has a wide range of application in Bayesian inference and physical sciences. Conventionally, we rely on Markov chain Monte Carlo. However, vanilla Metropolis-Hastings algorithm and its variant have difficulty for near non-identifiable and multimodal distributions. Sequential Monte Carlo method, which can be used to estimate the normalization constant, was developed to address the difficulty. However, the practitioner needs to design many details in a typical SMC analysis. Our research question is, suppose we consider a limit of SMC to infinitely many temper scales as a continuous time. Can we find a deterministic flow that transports the initial samples such that the flow-induced distribution coincides with the intermediate distribution prescribed in the continuous time SMC at any given time? If so, we can use the flow to transport the samples and achieve sampling the target distribution at terminal time, replacing the required detailed design of the transition kernels in the typical SMC. The main contribution of our work is outlined in this section. We first established the evolutionary equation of the flow field given the SMC annealing schedule in the continuous time setting. We proved that under some mild conditions, there exist solutions of the PDE, but the solutions are not unique. However, all we need is to identify one solution and use it to transport the samples. However, this can be a high-dimensional PDE, which does not have an analytic solution. Our proposed strategy is to transform the problem into a self-learning problem, where we will use a neural net to model the velocity field. We will use automatic differentiation to compute the divergence of the flow in the equation. In addition, the score function as well as the ddt log rho tilt term in the equation can be computed from the unnormalized density function. The average term here can also be estimated using samples. Assuming samples at time t can be drawn, our aim is then to minimize the discrepancy, here defined as a L2 loss of the difference between the left-hand side and the right-hand side of the PDE average over samples. Once optimized, the neural velocity field can be used to transport samples to a later time, t plus delta t. These samples can be used in turn for training the velocity field in a later time. Recursively, we can train a series of a neural network that transports samples from the initial distribution to samples of target distribution at the terminal time. The strategy only works if the neural networks perfectly characterize the solution of a PDE and perfectly transport the samples to a later time, which in practice is never possible. We perform a more detailed analysis to treat the distribution induced by the trained neural network as the proposal distribution of an importance sampler and establish a surprising fact that the importance weights are related to the cumulative error defined as the right-hand side minus the left-hand side of a PDE integrated over the sample trajectory. Using the importance weight, we prove that we can unbiasedly and asymptotically estimate both the log normalization constant as well as the normalization constant. Here, we highlight the key differences between our proposed approach and similar technologies. First, in comparison with physics-informed neural networks. In our proposition, the equations is evaluated on samples transported by previously trained neural networks in a principled manner. In terms of the physics-informed neural network, it evaluates the equation on sensors that are defined in an ad hoc fashion. Our proposition uses importance sampling for correcting the imperfect neural networks, while vanilla, PIN, or physics-informed machine learning does not. Compared to neural ODE, our objective is to solve for equation 1 over the course of the entire transport. In terms of a neural ODE, the objective is to maximize the likelihood at the terminal time. Compared to a recent technology called flow matching, flow matching's objective is to match the neural flow to a given target flow. In our case, we don't have the target flow, but instead we're given the PDE and we know that the velocity field must satisfy the PDE. Compared to other generative model enabled sampling methods, the first one is a neoflow transport Monte Carlo. AFTMC mixes Monte Carlo step and normalizing flow and use end-to-end maximization of the likelihood. In our case, we use only flow to transport the samples based on enforcing the PDE. In comparison to path integral sampler and denoising diffusion sampler, both PIS and DDS use diffusion models to stochastically transport the samples, while our approach uses deterministic flow. PIS and DDS only fit the terminal distribution, and in our case, we fit the entire anneal path of the distribution. On a set of standardized test problems, which include 2 analytical distributions, 2 Bayesian logistic regressions, and 2 other problems, we show that our method outperforms other generative model-enabled samplers. Thank you very much for your interest.